Hello, everybody. My name is Rez Mani, and I work for Allied Scientific Pro. And today's webinar is about laser testing of single event effect, or SEE, and case studies. This webinar is being recorded, and the recording will be sent to you within a few days. I also have my email written down here at the bottom. If you have any questions, you can send me email. Also, we have a Q&A session at the end. If there are any questions, I'll be glad to answer them. So let's look at the topics. What are we covering? We'll be covering some basics as well, in case someone is not familiar with the basic concepts. We are going through some basics. So we start with what is single event effect, and then we will go on to describe different types of single event effect, and also the needs of satellite instrument to get tested for the SCE. And then we'll just go into comparing different methods of single event effect, methods of testing. There's a radiation testing, which I'm sure many of you are familiar with, in a particle accelerator, and then the pulse laser testing, which is what we offer. There are different modes, the single photon absorption and two photon absorption for the optical method. And we can also discuss the pros and cons of pulse laser testing versus radiation testing. Then we'll go a little bit and talk about the Axicon lens, which is a new topic in this SCE community, and calibration correlation. And then we'll describe the Allied Scientific Pro's pulse laser C testing system. It's a lab we have here for single event effect that anyone could come and use the facilities, test their equipment. We talk a little bit about the wide band gap semiconductors such as gallium nitride, silicon carbide, and gallium arsenide, and what lasers are required for testing these semiconductor devices that have a wide band gap. And then probably the most important part of the webinar would be some of our own C testing in the SPA lab. We've tried SRAM HM6504, and we observed SCU, and we also attempted to get SCT in op-amp LM124. I'll explain what these are in detail. So moving on, what is single event effect? Just again, explaining the basics. So whenever a charged particle is hitting this electronic circuit, it could be a proton or an alpha particle, or even an uncharged particle. It strikes the electronic circuit and it generates these electron hole pairs along the way. And you can see here this red particle is generating this electron hole pair. It's going through the bulk of the material. This darker green is the sensitive part of the circuit. These are the metal pieces, and this is the bulk. So this could potentially disrupt the operation of the circuit, or it could even destroy the circuit if the energy is too high. Now, these satellite instruments, they carry many electronic circuits and devices, and these electronic devices, which I mentioned them here, they get bombarded by the charged particles from the space, and they could get damaged, or their operation could be disrupted. So all these analog to digital converters and EEPROMs, FPGAs, SRAMs, microprocessors, they're all susceptible to bombardment by charged particles in space. So they need to be tested prior to launch, and the managers have to decide if basically there's a need for radiation hardening or change of design. And the sensitive nodes of these circuits have to be identified clearly, and measures have to be taken to basically remove this sensitivity by either hardening or change of design. So let's look at the origin of these charged particles. What are the origins? So one source of these charged particles is cosmic rays. So a stream of charged particles from outside of solar system and distant galaxies, including protons and heavy ions. So if there is, say, a supernova explosion somewhere in a far galaxy, the charged particles from that explosion could come and enter our solar system and reach the Earth. So that's the source of the charged particles. The other source of charged particle is our sun, which emits a huge flux of charged particles, which include protons and heavy ions. And these especially become more intense during solar flares. Some of these charged particles, they are trapped in the Earth's magnetic field in Van Allen belts, as you can see in this picture at the bottom, and they rotate constantly around the Earth. When a satellite is launched, it has to pass through these belts and get bombarded by these charged particles. And the third source of the charged particles is secondary particles, which is generated when a charged particle is colliding, a cosmic particle rather, shown by this white, you can say glow, collides with the atmosphere, and the cosmic particle generates secondary particles like neutrons and protons. You can see the cascade of all these particles falling. So some may ask the question that how is this possible, because our atmosphere extends till 100 kilometers or up to 100 kilometers above the surface, and there's no satellite that basically flies there. So, but actually recent studies have shown that Earth's atmosphere extends a few thousand kilometers above the surface. And especially for low Earth orbit satellites, they could fly anywhere between 160 to 2,000 kilometers. And there is atmosphere there, and there is bombardment by charged particles. So secondary particles are generated at this height that satellite is operating. All right, so what are the types of different single event effects? So we have the non-destructive type, which include the SCU, single event upset, SCT, single event transient, SEL, single event latch up, and SEFI, which is single event functional interrupt. And looking at the diagram on the right-hand side, you can see the SCU is single event upset, which happens mostly when a value of a cell in an SRAM, for example, flips from 1 to 0 or from 0 to 1. So change of state. And here charged particles striking, and this is changed from 0 to 1. And over here, you can see charged particles has set a pulse, a transient pulse, which we call a single event transient. And this pulse is propagating down the circuit and reaches another SRAM cell and flips that value from 1 to 0. So one could cause the other. So I'll explain in detail what are the other types of non-destructive in the next slide. We also have the destructive single event effect, such as the single event latch up. So you have it either non-destructive or destructive, and single event gate rupture, SEGR, and single event burnout, SCB. So let's go into more detail about these different effects. So I already explained the SCU and SCT. It's a transient pulse that flows down the circuit. So what about the latch up? It's always exclusively is accompanied by increase in the current. So in case of when you have increased current, when a charged particle increase hits the circuit, and then it causes an increase in unusually high current flows, that is a sign of SEL. It could be destructive or non-destructive, affecting mainly CMOS devices. And one could basically remove this. If it is a non-destructive SCL, a power down followed by a power up will remove this unusually high current. But if it is a destructive, then that reboot will not make any difference. We also have the single event functional interrupt, where it's actually a severe SEU. So there are a condition where there are stuck bits and device stops normal functions. The control circuitry of the circuit places the device in a halt or test mode, and it's undefined. So it requires a power reset to recover. I will show you some example later. Then we have the destructive type of SEE, and the most important one is the single event burnout. And here on the right side, you see a burnout in a 120 volt DC to DC converter, where the striking particles were so energetic that they just burned this DC to DC converter, completely fried. And over here, you have a neutron-induced single event burnout of a silicon carbon power MOSFET. So completely destroyed. And then, as I mentioned, the single event latch up could be destructive as well if the power reboot does not fix the problem. The large current would eventually destroy the device due to thermal effects. And the last one is the single event gate rupture, which happens in MOSFETs. So the electric field due to these generated charges due to the SEE would add to the gate and will short out the gate. And this way, the MOSFET is completely destroyed. So in fact, it turns out that the SEGR is the only SEE effect that cannot be tested with the optical method. It can only be tested with the particle method. So let's move on and understand what is the need for testing the satellite instruments prior to launch. So as we mentioned, we have to specify and understand where are the sensitive nodes of the circuit. Sorry. So the right-hand side, you have the SCU sensitivity map. You see this is a SRAM cell, and you can see the outline of the circuit, and it has been bombarded by pulse laser, for example. So these are the sensitive spots in the circuit. So what's the difference between the colors? The red color is the most sensitive spots, and they are triggering this SCU sensitivity with a low energy. The yellow ones are less sensitive and they require more energy to trigger the SCU. So this way one is mapping the SCU sensitivity of a circuit. And one has to think about, is there a possibility of redesign without additional charges and money to be spent to do radiation hardening? Maybe just a simple redesign of the circuit would remove this this sensitivity. And this has been done in some aerospace projects. I've read in some papers that a simple redesign of the circuit has removed the sensitivity. If not, then there are other additional measures one can take, such as radiation hardening silicon on insulator SOI or silicon on sapphire SOS, which you could put additional dye on top of the sensitive part of the circuit and try to protect it against the strike of the charged particles in space. So let's look at the method of radiation testing for SEE. So this is done in a particle accelerator facility. And here, for example, you can see a long tube where the charged particles are being accelerated by a very large electric field, and then they go into a chamber that is under vacuum, and they will strike the electronic circuits that are mounted there inside the chamber. So what are the pros and cons of this is, first of all, it's more realistic of the space environment, because what is hitting the particle, the electronic circuit, is charged particles. So here we are also using charged particle. It penetrates the metals. A lot of circuits have metal pieces on top, so charged particle could penetrate through the metal. And one can do measurements of absolute values, which we'll get into later, such as absolute saturation cross-section, upset threshold, and error rates. So whatever you need to measure, you can get the absolute value using the particle method. On the downside, it is an expensive method. It requires thousands of dollars per hour, and it's very localized. Sometimes you have to travel thousands of miles to get to a radiation facility, and it's hard to get the time booked. Is usually very busy, and I'm pretty sure those of you who are in the aerospace industry and business know that it's hard to get the radiation time. Sometimes you have to wait for about a year. It may damage the circuit permanently because of the energy of the charged particles, and it does not penetrate thick protecting insulating layers, such as is shown in the right-hand side. It's a flip chip package IC where the sensitive part of the circuit is at the bottom and is covered by this thick layer of dye, which is an insulating material. So it does not penetrate through this. So you cannot get to the sensitive part of the circuit. It also needs a vacuum for the measurement, because if no vacuum is created, the beam of charged particles will collide with air molecules and lose its energy. So these are some up and downs of this method. And now I want to show you a small video. It's a radiation testing facility in Finland, in the physics department of a university in Finland. And this long tube here is where the charged particles are being accelerated. And this is the chamber, which is under vacuum, and the electronic components are being mounted inside the chamber. So this video, I need to speak for the speaker because it's not possible to transmit the voice. So I'll run the video and then I will tell what he's saying. So let's look at the radiation facility, and I'll put it on mute. So let's look at that. So we are now in the university in Finland in the physics department accelerator laboratory, and this is the laboratory radiation effect facility. In this facility, they test electronic components, and they are one of ESA's test facility. We test here components against radiation which exist in space. We simulate the same effects, although we do not use exactly the same particles for those effects. We can make the so-called ion cocktails, so we can accelerate several ions together, 7 different ions. We can choose those ions one by one at the end of that acceleration process. So it is possible to use these 7 ions during one day. 7-day test can be done in one day, actually. We have 20% of beam time, which is available for this activity. That means about 1,000 hours a year. Our dream is to do the component tests by ourselves, and this is what ESA wants us to do, and that would be very nice because the companies come here personally, travel here and stay here for 2-3 days. They could send instead their components and we could do the test. For everybody, it should be easier. So here you could see the device. And these are different monitoring systems. So that is the video on the radiation facility. Let's go back again to our presentation. And let's go on now to look at the cross-section versus linear energy transfer, or LET curve, which is quite important when you take your electronic components to a radiation facility. You want to generate this curve. So the curve has the y-axis as the cross-section in units of centimeters square, and the y-axis and the x-axis, sorry, it is in the units of mega electron volts per mega electron volt centimeter square per milligram. So one has to explain why this strange unit is there. It's because the x-axis unit is derived from the energy deposited per unit length. So mega electron volts is the energy of the particle, and centimeter is unit length. And then you divide that by the material density in the units of milligrams per centimeter cube. So centimeter will cancel out, and this centimeter square comes in the numerator. So that's how you get the mega electron volts centimeter square per milligram, which defines the energy that has been deposited by the particle. Now the cross section, it has dimensions of centimeter square, and how to calculate the cross section or how to measure it, it is calculated by dividing the number of upsets by the beam fluence in particles per centimeter square at a particular beam energy. So here, for example, you see these beams of particles are hitting the circuit, and there are only two of them that are causing upsets. So there are two upsets. So you would divide these two by the fluence of the particle, how many particles per centimeter square, and that will give you the cross section. And this is at a particular energy, so you could just then increase the energy and then get another point and get another point. So there are 2 points that are very important here. One is the threshold LET, which is the energy at which you could observe the C effect happening. It starts to rise, and then eventually it saturates. So the cross section where it saturates is the maximum amount of cross section you can get. It's called the saturation cross section. So increasing the energy any further would not give you additional cross section. So these two parameters are quite important, needs to be measured. So now let's look at the pulse laser testing. Now that we saw what the radiation is there to offer, we could look at the pulse. So in case of pulse laser testing, normally a picosecond laser of the picojoules or nano-Joules magnitude is focused using a microscope objective on the device. So it's a pulse laser of a picojoule pulse. And you can see it's reflected from these mirrors and goes through these microscope objective and is focused on this device, which is on an XYZ positioning system. And what we have here, normally there are two cameras, a CCD camera and a near IR camera. They're looking at because the beams usually are in near IR. You're looking at the device surface and also where the beam is. Very accurate positioning system of maybe about a 1 micron resolution. And you also have a fiber optic illuminator that shines on the whole device. So what are the pros and cons of this? First of all, it's pros, it's less expensive, and you don't need to go to the facility. You could buy the system. I mean, you can go to the facility, like we have a test lab here where you can come to us, but you can also purchase the system and take it to your lab. So you don't need to book a time to go to the facility. It does not damage the circuit at the lower energy levels, and it also passes through the thick insulating layer. Remember, we already explained that for the charged particle, it cannot go through the die. In this case, it can go through the die, but it cannot go through the metal. is faster and cheaper. And one very important aspect of this is that spatial and temporal information. It's possible to get spatial and temporal information simply because in case of particle testing, you have a broad beam and you could generate all kinds of SCE, but you don't know exactly where are these SCE generated. So, but in this case, you have a 1 micron beam, a focused beam of 1 micron, and then you would know at which point the sensitivity is happening and the SCE is being generated. You can also correlate the generation of SCE with the pulse of the laser. So you would know at what time this exactly has happened. So spatial and temporal information. You don't need vacuum for the testing, and it's also suitable for commercial off-the-shelf systems. You could purchase many pieces and test them one by one. On the downside, you cannot measure the absolute values, which we will talk about later, all the absolute thresholds and cross sections. So you need to calibrate this against a particle method. It's only a complementary method to radiation testing. It's not meant to replace the radiation testing. So basically what is used for is to first identify all the error modes and the sensitive spots, and then you take it for a calibration to a radiation facility. So this way you save on many, many hours of expensive radiation time because you've already identified where are the sources of error, where are the locations of the error, and then you could save time and money when you go to the radiation facility for calibration. So let's explain a little bit of very basic physics in here. We need that to get into the choices of lasers we will be making for different semiconductors devices. So basically solids are divided into 3 categories: a metal, semiconductor, and insulator. And there's a conduction band shown in green and the valence band shown in blue. So in case of metals, they overlap, and that's why you have a sea of free electrons. In case of insulators, this gap is too wide, so electron hole pair cannot be generated. Electrons cannot jump the gap to contribute to the conduction. In case of the semiconductors, this gap is quite possible to be jumped by an electron. So electron could jump and could leave a hole behind. So it could be possible for it to contribute to the conduction. In case of silicon, this band gap is 1.1 electron volt. And if a particle or a photon strikes the electron and has this energy, could impart this energy to the electron and could make it jump across the gap. So going back again to cross-section versus laser pulse energy curve, it's another similar curve to the cross-section versus the lead curve that was for the particle. And you can see here that it has a very similar shape. So by focusing a typical laser pulse of picojoule, a picosecond pulse width, and less than 1100 nanometer wavelength in case of silicon, to nearly a 1 micron diameter, you can get a similar curve as the cross-section versus lead. So the interesting part is that the relative values, the shape of the curve is the same. So if you could take the electronic circuit to a radiation facility and calibrate it, then you would know how much picojoules, for example, corresponds to how much mega electron volt centimeter square per milligram. And then all the follow-up measurements could be done with the pulse laser instead of the particle. So for simpler chips in the past, there are a lot of papers that talk about converting the x-axis values from picojoules to the units of lead. but certain conditions should apply, and these are very approximate equations. So some very famous authors such as Stephen Buckner and McMaster, who are pioneers in the field, are trying to correlate these two by using some equations, but best is just to calibrate against radiation. So for the pulse laser testing, you can see the energies are in picojoules here. How to measure the cross section for this? So you have to move the beam across the circuit, and it's better to have a short or a very small, preferably a 1 pulse per second beam, or basically pulse repetition frequency. So each point would only throw 1 pulse at a particular point, and when the pulse is hit, you move on. And then you see that if this has generated the SCE or it hasn't generated the SCE. So I'll explain that later when I show the results of our SRAM testing. It becomes more clear. So let's look at the penetration depth in silicon. It turns out the penetration depth increases with increasing wavelength. So here in the UV, you have very low, this is in micron, less than 1 micron. And then when you get to near infrared, say 1030 nanometer, you have a few hundred micron. In case of 1064 nanometer, the neodymium YAG laser wavelength is 676 micron, and for 590 nanometer, it's only 1.7 micron. So laser pulse can penetrate inside these insulating layers, but one has to make sure that the thickness of the insulating layer is less than the penetration depths of the laser. If the thickness of the insulating layer is more, then one has to do some polishing and basically removing some of the material so that it becomes less. So thinning is required, basically. Thinning and polishing is required if the insulating layer is too thick, because otherwise the beam, in case of a single photon absorption, which I'll describe later, would not reach the sensitive part. Here is another plot. So 1.1 electron volts correspond to 1160 nanometers. So you can see that the absorption coefficient is decreasing with increasing wavelength. And after 1.16 micron, it just drops to 0. So you cannot excite, with 1 photon, you cannot excite an electron to jump across the gap. And it does not absorb any further. All right, so let's go into more detail in describing the single photon absorption, SPA, optical excitation of carriers. So here you can see on the right side the band gap and the wavelength of 590 nanometer is hitting and is generating the electron hole pair. So all of this is described by the interaction of radiation with matter equations that are shown here in this blue box. And there are 3 equations. The second equation we would ignore because that equation has to deal with the intraband excitations by free carrier absorption. So by that we mean whatever carriers they are jumping to a higher level within one band. So we don't really need to go into details in the second equation, but in case of the first equation, what happens is in case of single photon absorption, you only consider the first term, which is this alpha, this absorption coefficient, and I is the energy, and this is the energy gradient, basically. So the other terms we can ignore because their coefficients are too small. And this sigma EX here is a free electron absorption cross-section. We can ignore this term as well. So only the boxed one is taken into account. And this turns out to be nothing but the Beer's law of absorption. So I is equal to I naught e to the minus alpha z, which is the Beer's law of absorption, so exponential decay of the beam. And this exponential decay is also observed here, that the beam basically gets weaker and weaker as it goes through the material. It deposits these charges. The red area is showing the charges that have been deposited, and the contour here is where 63% of the charges have been deposited. So that's why we call it the 1/E contour. So for a shorter wavelength, 590 nanometer, this is of the order of probably 2 micron. For 800 nanometer, this is about 6 or 7 micron. So the propagation of charge is in 2 dimensions in this case. So it's in a linear XY plane, and penetration depth increases with increasing wavelength and is defined as 1/alpha. So whatever alpha is, 1/alpha would give you how deep it could go into the material. The third equation also shows the rate of change of the deposited charge, which in case of the single photon absorption is directly proportional to the intensity of the beam, which is I. So it's a linear effect. Here is another look at that. So you can see at 800 nanometers, you have about 7 micron penetration depths. And we had seen this before also. If you go back to one of the plots, you can see at 800 micron, the absorption coefficient is about 10 to the 3 centimeter inverse. So 1/that would be nearly 10 micron. So this is consistent with this plot as well. Only the units are different. Okay, so the next thing that we will be talking about is the effect of pulse width. Excuse me 1 second. Yes, sorry about that. The effect of pulse width. So you could see that there is 3 regions here in this plot. So you have 100 femtosecond to 30 picosecond region on the left side. In the middle, you have 330 picosecond to 8 nanosecond, and then you have past 8 nanosecond. So the question is, could we use any pulse width for doing our C testing? Or is there a particular requirement for pulse width? So the answer is, if you have a very short pulse width, between 100 femtosecond to 30 picosecond, it doesn't matter what it is. And you can see threshold pulse energy is very low. So it doesn't change. When the pulse width increases from 30 picosecond to 8 nanosecond, there's an exponential rise. So you would need more energy as the pulse width grows. And past 8 nanosecond, there's a sharp linear rise. So you could get the single event effect at larger pulse widths, but you would need more energy to get them. So the other requirement is also that the pulse width should be shorter than the response time of the circuit, because if it is too large, then this is larger than the response time of the circuit, you will not see the complete effect. So it's not completely done, and the circuits have to respond. Usually, the pulse width is much shorter than the response time of the circuit. All right, so let's talk about the backside, front side illumination in case of SPA. So if you have a circuit that is not completely covered by metal parts, like in this case, you can do a front side illumination for SPA, no problem. So you could get to the sensitive part of the circuit. But most of the circuits these days, especially in case of the flip chip configuration, they are covered with metal pieces, and you have to go through the backside. So you can see the laser beam is focused through the backside, has to go through the die, and gets attenuated while it's going through the die to get to the sensitive part of the circuit. And this is where the calculation of penetration depth comes into picture. So if the penetration depth, as I mentioned, is larger than the thickness of the die, is no problem. But if it is smaller, then you have to do some polishing and thinning. And you can do that in a workshop. You can just get some CNC machines and polish and thin the semiconductor till you get to the desired thickness. So now let's look at the two-photon absorption. So how does that work? So as I mentioned, past 1160 nanometer for silicon, you can't get a single photon absorption. There's not enough energy. But if you could focus the beams to very, very tiny spot, and if you have a very high peak power, which means a very short pulse width of the femtosecond, order of femtosecond, then two photons could put their energy together, add up their energy together, and could excite an electron to go to the valence band, to the conduction band, sorry. So in this case, if you go back to the equations of interaction of radiation with matter, the term that becomes significant is the third term. So this beta is the TPA coefficient. So you could see it's a nonlinear effect because di over dz is proportional to square of the intensity. So this is one difference. It's a nonlinear effect, and the rate of deposition of charges also is proportional to the square of the radiation. This term we can ignore, and the second equation we can ignore as well. So usually wavelength should be such that energy is less than the band gap. Typically photon energy should be slightly greater than half the band gap. So you would put two photon energies together to have enough energy for the electron to cross that the band gap. It's definitely a nonlinear process, so one has to look at the consequences of this nonlinearity, which I'll explain later. So here you see in this picture on the right side that the electrons are not being generated throughout the bulk because you're going through the backside, and only when it gets to a very tight focus, shown by this little red region, the two-photon absorption effect takes place. The distribution is not in an XY, but it's in 3 dimensions. So you can see this is where the focus has been made, and it's propagating in 3 dimensions. So backside illumination is easier than SPA because there's no waste of energy in the bulk layer. So only you get the TPA when it reaches the sensitive part of the circuit, when it's at the focus. The pulse width is very short, typically 120 femtosecond. And the other good part about it is this narrow beam that is generated, and it's very similar to radiation testing characteristics. So let's compare the pros and cons of TPA as compared to SPA. So what are the pros? There are large penetration depths for TPA. You can go and inject, depending on the focal length of the microscope objective, you could inject at any depth. You could do 3D imaging. It's more similar to radiation testing. Backside illumination is easier. On the downside, the resolution of the microscope is lower due to laser wavelength. This is to do with the diffraction limit. So the larger wavelength will have less resolution. And the cost of the femtosecond laser for TPA is more. So, and then the other issue is that because the deposited charges depend on the level of illumination at that point where they're being generated, if there is a little inhomogeneity or in the backside of the semiconductor or a small fluctuation in laser intensity, then this significantly changes the amount of charge produced in the sensitive volume. So for TPA testing, one has to make sure that the backside is completely polished and uniform, and also one has to have a control over the laser intensity, because you don't want to deal with the consequences of a nonlinear effect and generate strange results. So let's summarize what we learned for different parameters. Wavelength, again, past 1.16, you can't generate single photon. Focusing size as a result of diffraction limit increases with wavelength. Pulse duration, we described the 3 regimes. You can still get it past in the nanosecond region, but you need more energy per pulse. You need more photon energy. You need more pulse energy, basically. It should be shorter than the response time of the circuit. Otherwise, you would not, if it is a very long pulse, then you can't observe the full effect. Pulse energy, normally for SPA systems, anywhere between 100 to 3,000 picojoules. So normally we're talking few 10 to 100, depending on what you want to test. Some effects require less energy, but in the picojoule order. But for TPA, typically 20 nanojoules. So SPA is preferred for analog circuits. Analog circuits require more energy than digital circuits. So maybe if for testing an SRAM, you need 10 picojoule. For testing op-amp, which is an analog part, you may need up to 1 nanojoule. The spot size is diffraction, limited by diffraction. The smaller it is, the higher is the resolution. Typically, it's about 1 micron. Correlation of laser measurement to ion beam measurement. I mentioned that some of the pioneers of the field, such as Buckner, in this 2013 paper, came up with this formula to correlate the two. You can see the shape of the two curves are very similar to each other. Here, E0 is the incident energy. This is the energy being delivered to the sensitive spot. EP is the pair creation energy, and E gamma is the photon energy, what is actually generated by the laser. However, these are all approximations. So some experiments that have been done on CMOS, SRAM, and bipolar logic circuits found that the pulse laser could give consistent values for upset threshold, and basically these thresholds could be correlated to ion beam thresholds. The relative upset values correlated well with the ion beam. So basically it's just a matter of correlating these two curves together, which is possible with a trip to the radiation facility. Laser could be used for quantitative measure of linear energy only if one time the validation has been used with a radiation facility. If all the follow-up measurements can be done with the laser. For calibration, it's better first to do the testing using the pulse to identify the nodes and the sensitive nodes to avoid ion damage, because ion could potentially damage the circuit. So better first to do the laser testing and then go to the radiation facility. Now, a new topic here which I want to introduce is the use of Axicon lens in the TPA mode. So Axicon lens, which is shown in here, it has this conical surface and it has this angle alpha. It's characterized by this alpha, and what it does is that it will elongate the beam. So here on the left side, you see the heavy ion charge track is very narrow, and in case of TPA, you can see with 100 times microscope objective, you only could get the focus at this point. It has to travel through 100 micron and get focus at this point. But in case of Axicon lens, if that is used, one could get an extended beam. So the charge track that is left by this beam is very similar to what is left by a heavy ion. So it's narrow and long. It produces a very narrow and long image, typically 1 micron by 800 micron. So what are the advantages of these? It emulates an ion charge track much better in a TPA mode. And also, it's not so sensitive to focusing, because here there's a lot of sensitivity to focusing to get that effect. But because this is so much extended, you could move it up or down, and you will illuminate that sensitive spot, because this long image would cover that part much easier than this tiny spot. So there are these advantages of using Axicon lens to generate the TPA effect. Okay, so now let's go back to some of our system, introduce our system. So Allied Scientific Pro made a SPA laser testing for an aerospace company. It delivered in 2017. It has the upgrade to be potential to be upgraded to a TPA system. And then recently, before we talk about our recent system, this is the main components of our system. You have the 4 subsystems: the laser, CCD, illuminator, an objective. So all these components are here, and there's also a translation stage, very accurate translation stage. So I'm not going to spend much time on this slide, because instead I'm going to show you a video. The only thing I want to emphasize here that there are 2 cameras, a visible CCD and there's IR CCD. The illuminator also, fiber optic illuminator, has 2 wavelengths, as visible wavelengths and near IR wavelength. So there's a video that I'll show you where our company CEO, Mr. Steve Lavoie, describes our SPA test facility. And this video, I'm going to play it. Again, there's the issue with the voice, so I have to speak in place of Steve. So I run the video and I will speak when he's talking. Hello, my name is Steve Lavoie from Allied Scientific Pro, and today I'm introducing the SPA test facility. This is our C testing station. We put together a system in our lab in Canada, so you're welcome here to do some testing of your IC chips. And we also build those commercial systems as well for our customers. So we do offer a service and also a system. So just a very quick summary of what we have here. We have an XY stage for a very rough adjustment, all motorized. We also have a manual, very fine adjustment with tilt. And we have a very precise focusing stage as well to focus underneath the microscope objective to see clearly the IC design. And over here, underneath here, you have all the microscope accessories which are protected from people. With the microscope objective, if you use Mitutoyo microscope objective is a quick release, 100 times. And there's also a camera in shortwave camera that one can see the silicon, and also one visible camera for very quick alignment. And the same with the light. We have a two sort of light source, one for illumination of the microscope, one invisible, and one in the short wave, so you could image in both the spectrum. The laser is underneath there. So in this case, we use a picosecond laser in case of our SPA, but we can also have a femtosecond laser with OPA. So we build this system for TPA testing. You have full control access by computer of all these devices and testing gears. So that's a very short summary of our SCE system. And I hope this information is useful. You're welcome to come here and test your devices. All right, so that was an introduction by Steve about our SCE system. So let's move on. This is like the table of specs from each system. What is important here is that for the SPA system, the wavelength is 1030 nanometer in near IR. And usually you have picosecond, although it's mentioned less than 400, but it could be picosecond for the SPA laser. For the TPA laser, you have an additional component here, the OPA, optical parametric amplifier, that could generate wavelengths between 630 to 2600 nanometers. So this is acting as a pump laser for the OPA, and so one wavelength could be selected in between. The system is designed for one wavelength in this range. So that is one thing about the ASP's laser system. So one quickly, lasers for C testing of wide bandgap semiconductors. So for gallium arsenide, the bandgap mentioned in this column corresponds to 870 nanometer. The Thai sapphire laser would work for that. For gallium nitride, it's in the UV, an excimer laser could work for that. And for silicon carbide, second harmonic neodymium YAG could work for it. So these are also possible systems. So let's move on to the last part of our talk, which is probably the most important part, and talk about the testing, the C testing that we did in our SPA test facility. The picture that you can see here is a picture of one part of an SRAM. It's a 64 by 64 matrix. And this material is taken from a paper by McMaster, who tested the same piece. So I've made it inside a box. I've outlined the boundary of one cell. And you could see these metal pieces here that are covering this cell. So the idea of testing is that one has to shine the focused beam. So let's say the dimension is 100 by 100 micron, and your beam is 1 micron square. So, or diameter of 1 micron. So you would just shine it at one point at a particular energy, and then see if you get the flip. So if the state changes, then that's the SCU. So then you reset the circuit. You reset the cell from 0 to 1. So initially with 1 was dropped to 0. Now set it back to 1, and then move the beam to another point. And then this way you have to cover the whole area of this cell. I mean, obviously you can't go through the metal, so this shining the beam on the metal part would not give you anything, but you can go through the other parts, and you can see that with increasing energy, so here there was only 1, increase the energy to 7.2, there was more, and then 10.4, there was more, at 20 picojoules, this is the maximum that you could get. So the total areas shown in black could be summed up, and then that is the cross section that you can get. So you can just change the energy and repeat the same experiment and generate this kind of curve, the cross section versus the picojoules. So this is in the unit of centimeter square. So what did we do? We tried to repeat the same experiment using the same cell. So the first step was decapsulation of the cell, which we did only by mechanical means. We used the side snip plier to decapsulate the cell. And you can see these are the two regions where all these little cells are. Then you have to connect that to a microprocessor and write a 1. We wrote a 1 to all the cells. And the issue that we had is that we could not get 1 pulse per second. The laser was not generating that. So you have to sort of synchronize your XY stage so that 1 pulse hits 1 point, then you reset, then you move on to the next point. So for this reason, we actually decided to remove the microscope objective and shine a broad beam onto the device. So the beam would actually cover the full device. And after we reread the values, there were about 10 or 11 cells that were upset. So all the values were 1 initially, and then these cells were showing sensitivity. Their values dropped to 0. So we confirmed that the SCU happens, but because the repetition rate was more than 1 hertz, some may have been upset and then went back again to its initial state. So we need to do more careful studying here and basically try to sync the output of the laser to the translation stage. So each point would get only 1 pulse. Then you would change the energy and move on to the next point and do another set of measurements. The other experiment we did was decapsulating the LM124 op amp. So this needed more energy from the laser, and we tried it. You have to mount that in a follower circuit and use a very sensitive or fast picofarad probe. So there was a paper by McMaster and Buckner that described testing of this. We actually identified the sensitive spots here with our camera, you can see, and then we moved around the beam, but we did not observe a set pulse happening, and this could be due to triggering issues because your laser should be triggering the scope, and we didn't get it, but we'll be doing this experiment again more carefully, and hopefully we'll show that. So let's go to the conclusions. So what did we learn from this talk? First of all, that the laser pulse testing of C is just a complementary method. It's not to be replacing the particle method because it cannot get the absolute value. So you need to do 1 radiation testing for calibration. What is good about the optical method is that you could identify the sensitive nodes of the circuit, the error modes that you get, different types of errors that you get, and this will save you time and money when you go to a radiation facility. Now, we compared TPA and SPA methods together, and we learned that backside illumination is easier using TPA, although TPA is more expensive. 3D mapping is also possible with the TPA, which is not possible with SPA. And hexagon lens could also be used to get a larger beam. So it's more similar to radiation testing if you have TPA plus an hexagon lens. Then optical C testing systems, they are faster, they're cheaper, and they could be brought to your location, and they're good for testing commercial off-the-shelf devices as well as any particular devices you have. And finally, SCU was observed at ASP's SPA lab for the SRAM HM6504, but we could not generate the curve of cross-section versus pulse energy, and it needs further testing for generating that curve. So with that, we come to the end of the webinar. I thank you very much for listening, and there is also webinar feedback that will be sent to you if you have any further suggestions, you need any improvement, or if any parts were not clear, please let us know by giving us feedback. And if you have any questions at this point, I will be glad to answer your questions. You could type the question or you could unmute yourself and let me know.
Hello, this is Jeffrey Prinzi from KU Leuven University in Belgium. First of
Hi.
all, thank you very much for your very nice presentation. I have a question on the Axicon lens.
Right.
So you mentioned this is for TPA.
Yes.
But my question is, do you need a higher laser energy to get the same spatial charge generation compared to a focused TPA?
Just a minute. Let me actually go there. 1 second. I'll bring up the lexicon. I don't think that you would, well, if you think about it, actually, if you use the same laser energy in these two cases, right? So the energy density would be much higher in this case than in this case, right? Because you're sort of like demagnifying in a way, right? So you would need more energy to have the same energy density, or you know, in this case of Axicon laser. This is my best guess.
Okay.
But that is achievable. Our lasers, the lasers that our systems have, they have plenty of energy. So increasing the energy level is not a problem.
Okay. And you stretch it out in the Z direction here.
Yes.
Does the let's say the volume, does it also stretches out in X and Y direction, or is it only in Z direction?
I don't think the volume changes in X and Y direction, because you can even see here, you can compare these two together, right? So you can only see either X or Y here, but in one dimension, this is almost the same thickness, right? It's only the Z that has been elongated.
Okay, thank you very much.
You're welcome. Thank you for your question. Any other questions? Are there any other questions? Going once? Going twice? Okay. So once again, I thank you very much for attending this webinar. And as I said, the recording will be sent to you, and feel free to contact us if you want to come and visit our radiation facility, or sorry, our laser pulse facility for testing. You could rent the laser time and the facility and do your testing. Or if you want to get a quotation or want to purchase either an SPA or a TPA system. Thank you very much and have a great day. Thank you, Jeffrey. Have a good one.